Lowercase or lowercase?
Lowercase?
You said undercase or lowercase.
Yeah, he said both.
It's 1.6.
I said undercase or uppercase.
Only the number.
Yes.
Hey, what about the 1/2?
What's that paper on the side?
No. Like, was that a bad? No. Okay, what about the 1/2?
It is 1/2.
So it's gonna be 4.6.
Wait, you did not square it? Stop. No.
Never mind.
Are you some kind of idiot, Cole?
Yes.
Whoa.
Hey, guys, everyone should have done 8.7.
Yeah.
Cole, get 8.7?
Yes.
Nate, 8.7?
8.6.
Well,
It's the grounded.
Round up. You're good.
I got it.
8.7?
Amen.
8.7? 8.7?
Amen.
I know.
Okay, alright, good.
What's the
Rewrite game for rollers.
Let's do it all at once now. What?
Let's go.
A joule is a Newton times a second, right?
A what?
Off, Elder.
A what? A joule is a
Joules the units.
It's Newton times a unit, yes. It's a Newton
It's
times a unit.
joules the units.
Yes.
What is a joule?
Alright. Yes, sirree. Alright. First off, when I say something conserved, I just mean that it remains constant. Okay? So when I say energy is conserved, that means overall I have the same amount of energy at the beginning as I do at the end. Does that mean the energy stays the same?
No.
No. It can change forms.
Do that again? Oh, okay, never mind, got it.
Is money conserved?
Yeah.
Did it change forms?
Yes.
Okay?
That is some deep. Or it is.
It is conserved.
Okay, yeah. It
It's
is.
changed forms. Okay? Now. This is where it gets fun. There's mechanical energy, the sum of the kinetic energies and all the forms of potential energies associated with the object or group of objects. So if I were to write this out a little bit more, it would be the sum of the kinetic energies plus the potential energy due to gravity plus the potential energy due to the elastic. Up to you.
What
Oh,
is
yeah, we
energy?
talk about mechanical energy.
So mechanical.
Don't even talk like that.
I appreciate this.
And actually, we're going to do the fact that mechanical energy is conserved. Now, let me make this very clear. It is only conserved in the absence of friction.
Just like what?
That's a test question.
No, wouldn't it also be conserved if it's calculated?
Only conserved.
Oh, no.
Well, the total energy is conserved, but not mechanical energy. So, like when you have friction, you lose energy in the form of sound and heat energy. And that's not in the mechanical energy equation. So mechanical energy is not conserved, but total energy is always conserved. That's the first law of
What did you say?
thermodynamics.
Let this be very clear.
He said only conserved in the absence of friction.
Mechanical energy?
Mechanical energy is only conserved if you have no friction. And that would assume air resistance friction as well.
So doesn't that mean like never?
Yeah. In reality, yeah. Yep.
So
Just making sure on the
mechanical
same
energy
So we're not
is
doing any
total
calculation
energy right now?
No.
Well, then isn't kinetic energy plus potential total?
No, but there's other energy forms that aren't those. Like thermal energy, acoustic energy, electromagnetic energy. Those are other energy forms that don't make up mechanical energy.
So like when we did that lab, that wasn't actually the total energy.
In that case, it was because nothing was leaving in the form of sound or, well, some of it was leaving in the form of air resistance, but yeah. In that case, yeah, pretty much. Assuming you can say that the friction due to the air particles was non-existent. But now was the total energy perfect for all of them? No, they weren't exactly the same, which means, one, there was probably some experimental error, and two, there wasn't a resistance.
So then, that total energy would also be mechanical.
In this context, yes. But if, say we were rolling something on the ground, then you got friction, energy is going to leave in the form of heat energy, and that will not show up in mechanical energy being conserved. Yes?
So why does it say on the note bracket mechanical energy is often conserved when we just said that it's not? It's like never conserved.
In the absence of friction.
Is often conserved. Okay.
In the absence of friction.
I'm gonna have that.
Yeah.
So what you're saying is you wrote it down.
What?
Okay. In the absence of friction. Okay? Now notice, I have mechanical advantage, not mechanical advantage, mechanical energy initial should equal the mechanical energy final. So really, I should do this.
Okay,
Well, my
E1
head
equals-
hurts.
no,
I equals,
No, God, why? Why? My head couldn't see the I as an I. All I saw was an upside down exclamation point.
That's why your head hurt.
Actually, that.
whoa. So this is what we'll probably use the most.
You should have gone Spanish, I think.
The
Write
NEI,
that
all I
down,
see
man.
is.
Might want to.
Isaac, why?
I don't know. I can't see it as an I.
Isaac is broken.
Hey, Jesse and Cheyenne, are you paying attention to all the stuff I just
Yeah,
said?
we got it. My toenail fell off last night.
That's disgusting and I don't
Did
want
you really pick it up?
What did you
Yeah,
say?
this is your number.
No, I don't have that. Like, we need that on your card.
You were not paying attention,
The
one
whole
iota.
thing?
Yeah.
Oh, cream roast. Zing.
We need that.
Zing.
Oh.
Wait, why is it equals? Why is it equals?
Because
Because the total mechanical
Oh, okay,
energy
now.
should be conserved. So the these numbers are gonna change, but the sum of them should equal each other.
Yeah. Yeah. Why is that NEI look so much like
Yeah, I could.
Mr. Trevor, you should change your
Makes
thing
me wanna die.
to Zing.
I could change this to 1/2 MV squared initial plus MGH
Write down the whole
initial
thing.
plus
The whole thing.
1/2 KX squared initial equals, I could continue to do that, but I'm not going to.
Hey, has anyone seen that paper over there on the board that's signed by Jordan Parsons saying we're going to win one game?
two games.
Or 2 games, yeah.
Let's do a problem.
Was that like a bet or something? Okay.
We need to spend as much time going over these problems here.
Can you guys do problems? Okay, problem number 1.
Alright? So, we are going to use this idea that in a frictionless vacuum, mechanical energy is conserved. So we can say, that's the kinetic energy initial, plus the potential energy due to gravity initial, plus the potential energy due to elastic initial should equal, no, kinetic energy final, plus the potential energy due to gravity final, plus the potential energy elastic.
It's because it's all conserved.
So we'll complain about
Yes.
heat.
Now listen. Now listen. What I said is earlier is that conserved means constant. It can change forms and still be constant. $1 equaling 4 quarters still means that money was conserved. It just changed forms. So what you're going to see is these numbers will probably be different than these numbers, but the sum of them will equal each other. Because remember when I took this and it had a certain potential energy and I dropped it?
Yeah.
Now energy just changed to kinetic energy, right?
Correct.
Yes.
So it was conserved, assuming right before it hit the ground and lost energy in the form of sound.
Wait, why was it conserved?
Because the same amount of energy had a potential.
Because all the potential energy got converted to kinetic.
Okay.
Yeah.
And then until it hit the ground, then that was different. But we'll see.
Okay.
Okay? So, all right. I'm going to quickly read through this problem. Okay? And then we're going to kind of top. Starting from rest, a child zooms down a frictionless slide from an initial height of 3 meters. What is the speed at the bottom of the slide? Assume that the mass is 25 kilograms. You should be thinking up here, is there any elastic thing going on here?
No.
Okay, there is no spring, there is no bungee cord, there is no anything.
It's frictionless.
So you could say that this will be 0, and then this will be 0, correct?
Yeah.
Why?
Is there a spring or anything elastic in this context
Oh,
of this
just that
problem?
E stand for elastic.
Yeah.
So then KEI is 0.
Ah, notice something.
Remember the P.
This is really, guys, you're gonna want to pay attention here. You guys are screwing around too much. Okay? What you need to do in these problems is identify when these guys can be canceled out by the context of the problem. And it says, starting from rest. What does that tell you? Initial velocity is 0. What variable up here would this cancel out?
KEI.
Which KEI? There's only one. That's going to be 0. Everybody understand why that is 0?
Yes.
Anybody not? Yes?
No.
Does anyone not? Yes.
How do you know you're using this equation instead of the short?
Because it's what we're doing right now.
Oh.
That
The other one
was.
has to
Did
do
you
with
say
energies.
ME equals PE plus PEG plus PE?
It didn't ask for mechanical energy. What the giveaway here? I didn't mean that sarcastically. I just didn't know how else to answer it. With the context of this problem, we have initial and we have final. So the only way we would be able to solve it is using the conserved mechanical energy. If they gave us one situation and they gave us like mechanical energy, then we could just use that. But I'm going to tell you now, you're probably never going to use that mechanical energy alone equation. It'll always be in the form of conserved. Okay? I don't think you'll ever use it in the first form. Everything we're going to do up to this point is going to be using the law of conservation here.
Solid.
Yes.
Are we solving, so what is her speed? Are we solving for KEF?
We're actually solving for velocity. That's what speed is. There's another thing.
KEF?
What?
Is that KEF in?
That's KEF is kinetic energy final. It's going to be within KEF, but it's
There's
not
another
KEF.
equation we need to.
Yes. Let's just first cancel out all the things that we don't need. Guys, just let me finish. This will make sense when you just let me finish. Okay? There's another thing up here that is 0.
KEF should be.
No, it's right before. If KF is 0, we know what V is then. That would be 0, but it's not. Because it says, what is the speed at the bottom of the slide? We're not going to say when it comes to rest, it's right before it
Final.
stops.
If it stops.
Head foot.
Peg foot.
We're not saying it stops. We're talking about right before it stops. How fast is it going right before it stops?
What is peg?
What'd you say?
Peg foot.
Peg.
Peg.
Okay, what is
PEGF.
Why?
Final.
Why?
Because it's at the bottom of the slide.
Ah.
Are we assuming that that's like right at the ground then? Or
Yeah.
is it relative?
Well, it does say bottom.
So potential energy final is 0 because the height at the ground is 0.
So therefore.
So when you slide down the slide, you get to the bottom of the slide. What's your height above 0 level?
Nothing.
0. You're at 0 level. You're on the ground
Nice.
when you slide down the slide. So your M, G, H, your H is 0. This whole thing becomes 0. Right here.
Peggy equals Cap.
Now, we know we have potential energy initial. Why?
Hey,
Top
Because we're at a height of 3 meters, so we know we have a potential
we can
energy
do that one
initial.
equation.
You're zooming.
And we know we're going to have a kinetic energy final because we're sliding down the slide, and that's right before you hit the ground, or right as you're hitting the ground. What is your speed at that moment?
Tell me we can solve for Peggy.
So, we know this and this is an equation, correct?
Yes.
M, G, H, I should equal
KEF.
1/2 M, V,
Squared.
F squared.
Nice.
I took this, and it's equal to this. What this is simply saying is this potential energy, initial, is getting converted completely to what? Kinetic energy. That's like this. But what is the kinetic energy right as it hits the ground? Right before, yeah, it should be its max, right? So now, let's plug in. Now first, actually, let's not even plug in because what are these M's going to do?
Wait,
Cancel.
answer.
They're going to cancel.
Where'd you get the
Can we just
G?
Everybody loves to do that.
You want to put it all in?
Yeah, can you?
Alright, fine. Okay, so what did we say the mass was here?
25.
25.
Oh, so now we just take this.
9.81.
Then we just.
Yeah.
9.81.
3.
The height is 3.0 meters.
E equals PEG equals FG.
It's a frictionless slide, bro. You won't go fast. What do you mean you can touch a frictionless slide?
You go,
I got
woo.
Frictionless doesn't mean you can't touch it.
You see that we have every variable to find out what the speed is at the very end when you're sliding at the bottom of the slide?
What is MGH? Where'd that come from?
That's the potential energy due to gravity equation.
Why were you able to put the I on there?
Because it's the initial situation.
So could you use that, are you gonna use the same one for the F one over there?
Yeah, I would still use the same equation, it just would be under the final condition
Okay.
if it wasn't zero.
And
yeah.
same for K.
Yeah, everything. This and this is the exact same equation, just initial conditions, final conditions. Exact same equation, just initial conditions, final conditions.
And then,
Exact same equation, just initial conditions, final
and
conditions.
that's PEE, that's the last two.
Yep.
Okay, I just.
Yep.
How did you put MGH and 1/2 MPF squared together?
How did I put them together?
Yeah.
Set them equal to each other?
Yeah, make them the same.
Because mechanical energy is absurd. I'm assuming that we're frictionless, so all of the sum of my mechanical energy at the beginning should equal the sum of my mechanical energy at the end.
So because mechanical energy, you can put whatever you want to do.
Well, mechanical energy has parameters. It's kinetic energy and all the potential energies. It cannot be stuff outside of that, but we're not doing stuff outside of
Would
that.
you be able to feel a frictionless slide? Can you like touch it and feel it? No.
Yeah, how is friction work again?
By the way, the
Like,
opposing
can you
motion.
not,
Those
yeah,
ones,
Opposing
like-
motion.
couldn't you even like not put your finger on something and go as friction?
No, you can touch it, but I don't think you can feel
That's a great question. We're talking theory here.
Because you feel the water. Because you feel the opposing force. You
I mean, it's saying that it is completely smooth, so you would still feel it, I think.
You feel the thing or the force.
Maybe you'd be moving so fast that you couldn't feel it, I don't know.
And then you couldn't sit down and stuff because you just couldn't stop.
Yeah. Okay, so once we solve for this,
This is a classic potential energy and kinetic energy.
okay, can I show now that the 25 kilometers cancel?
Sure.
So 9.81.
I'm probably just never gonna do
Oh. Just never know what you're doing there.
Nice.
Actually, I'm not gonna divide by a half, I'm gonna multiply by 2. We all cool with that, so I don't have to deal with the divided sign?
That's what I did.
Okay, should equal VF squared, but I gotta get rid of the squared by taking square root.
Square root.
You're looking at this real janky there.
I just did it different.
Well, alright.
Did you just put everything?
As long as you got the right
That's
answer,
right.
it's fine.
Don't
Don't
worry
worry
about
And
it.
it gets the same.
What did you do?
I'll give you the same answer. There's multiple ways to do this.
I put everything in, even the 25.
Well, you see if you can understand that 25 cancels out, guys? You
Yeah.
see how it's less work that you have to do?
Yeah, but
Hit buttons though.
It helps me like, so
That's
yeah.
fine.
Then I'll forget to, yeah.
That's fine.
I just.
Doesn't everything cancel out? So it's just zero.
Yeah. All I'm doing is trying to write less, but, okay? So your answer, what'd you guys get?
7 points.
How many stick figures do we need? Yep, 7.7 meters per second. So that would be the speed right before it hits the ground.
Hit the ground running.
Okay? Questions here. Do you guys understand here how what's happening is we gotta figure out, okay, what variables do we have? Okay? There'll be some situations where you might have these two and this, or these two and these two. I don't know how you couldn't have any kinetic energy, but, okay? Well, I guess if you had to start at 0, ended at 0, but you gotta figure out what variables you have and what variables you don't, based on all the stuff that started, it's been building on itself, hasn't it? Okay, the stuff that we talked about earlier in this chapter, yes?
Is it possible to do like just a whole lot of substitutions with this stuff?
Why would you even want to?
No, like if they force you to do a problem like that. If
Yeah,
they
you-
force you to do stuff like that, is that what this means?
For what? Okay, let's do this one. Now, what this problem is doing is
Yeah. And then, same thing.
By the way, it's 0.0.
Kramer, we have flash this year.
Just imagine it all.
Yeah, that's really, really outrageous.
I love reading Spanish words and like it's like stupid acts.
Newtons per meter.
Somebody subject
6 centimeters.
It's 360 because it's a decimal.
Okay?
I can't roll my R's. I can't do a French. I can do a French word. I can't do a Spanish word.
Okay, here we go.
No,
We got a small little spherical thing.
A ball?
Yeah.
It's spherical.
I'm going to change that to kilograms right now.
0.01. And then also centimeters and also newtons per meter.
Ooh, yeah, we should probably change that
What the heck is
to
a
meters.
newtons per meter?
But that always is.
So centimeters
Wait,
would
is
be.
that constant?
String constant's always that.
Okay? So it says a ball is held to, sorry, a small ball is held to a slingshot.
No, I like holding up against it.
Is stretched. Now this is saying how much it is stretched, not its total stretched length. Read the context of the problem. So they gave us X.
So isn't that do we
They made it easy for us. So we need to take that and convert it into meters,
0.006. Oh, I just went. Centimeters, never mind.
right?
Yes.
No, it.
Yes.
That's killing.
Yes.
That's killing.
And then.
Okay, they gave us
200
The constant.
newtons per meter.
What is the elastic potential energy of the slingshot before?
200.
Find that one.
Is it
What?
0.36?
Okay, now I'm gonna try to do this with you guys more conceptual and less mathematical. Okay, we'll do some stuff mathematical. The first part, what is the elastic potential energy of the slingshot right before it's released? So I'm pulling it and I'm holding it.
So the distance.
What? No, it's really.
It's 0.36.
So your potential energy elastic,
Because it's 200.
not G,
Divided by 2x. Oh wait, no.
I like that.
1/2,
Although if you multiply by
200 is your K,
Times 0.06.
Square.
Then you get
what does that give you for potential energy elastic?
your 0.36.
Six.
Okay.
Okay then.
Okay?
How did we know that we didn't have to use that huge long equation?
Because it just wanted the potential energy elastic, that's it. It didn't want anything else.
Yeah, but in the other one, it just wanted velocity.
Yeah, but we had two different situations where we had to
We're gonna
use
Just
that
look at what you're
equation.
given. They don't give you
You're
much.
gonna have to
but
do that down because 2 and 3.
Okay?
I mean, theoretically, you could do that. Just everything is zero besides that whole thing. Isn't that how that works?
Yeah.
That would be.
That would work, but.
What is the difference between?
I know it's PEI is VDS.
So 1/2
Your mental
Exactly.
energy would be
mass
higher.
times velocity.
Peggy versus Peggy.
That's the difference.
Exactly is the difference.
I got P.
I said, what is the difference?
I know. The difference is before and after.
Yeah, but does it change the numbers?
Good question, we'll talk about that. Okay? Alright, so let me finish. What is the kinetic energy of the ball just after the slingshot is released? So I hold it, I stretched it, and just after it's released.
Zero.
Okay? It should be at its max kinetic energy, right?
Yeah.
Is that right?
Should be your.
So
I guessed. Wait, what?
Because your max kinetic energy is the same as your, because there's no.
Because I'm taking all of my potential energy elastic and I'm converting it to what?
Kinetic energy.
But if
Kinetic
it's
energy.
just after it's released.
Yeah, then, just after you're released, you're going the fastest.
Question.
So
I
there's
have to
0%
accelerate a little bit
energy
before it
fully
reaches.
just
Yeah.
kinetic.
I wouldn't get that.
Correct.
Now I could set this all up,
Oh, no.
Or you don't have to.
but I just want to show you conceptually how this works.
I know.
How did you know it's conserved?
Point
Hey.
five times.
Assume it's conserved.
Yeah, that's fine.
But it doesn't say there's no air resistance.
Peggy's mine, back off.
Hey, why is
I'm just gonna show you how this works out. Just give me a second before you start going crazy with all the questions you might have. Okay? At the very beginning, did we have any kinetic energy?
No.
Oh.
Okay, we probably have potential energy due to gravity at the beginning, depending upon where we were. But whether I have it pulled or released, isn't that all on the x-axis?
Yeah.
So far.
So did the potential energy due to gravity change from the beginning to my other conditions? So these probably weren't zero, but they didn't change.
Yeah, so they're
Like
essentially zero.
if I have, I don't know how to do the slingshot here.
Like the 25 cancels.
Careful, it's anything like your cannon, I don't wanna see it.
Okay, from here to wherever it's unstretched, let's say unstretched is like this location, I don't know.
Wait, is it assuming you're pulling it straight then?
Yeah. Yeah, you're not gonna assume that. Don't get caught up in this, don't ever think, unless, it would tell you if it were unnatural.
Is there ever a situation where it gives us an angle? Okay, good.
Yeah. Okay, so did my height change?
No.
Pay attention, did my height change?
No.
If my height didn't change, is my potential energy due to gravity gonna change?
No.
So this is where this would cancel out this if I did the math, right?
Yeah.
Because of.
So just get them out there.
Because of height, yeah.
Get the heck out.
So we're gonna say that cancels. It's not zero, but if this is 25 and this is 25 and I subtract the 25 over to this side, what does it do?
Zero.
Make no more 25.
Okay?
Alright.
So we have potential energy elastic at the beginning. Did we have any potential energy elastic at the end?
No.
Well, now that it's all converted to.
No, it's
And
all.
then-
Because it says just after the ball was released or right when you get to back to your relaxed state. So what did potential energy completely transfer into?
Kinetic energy.
So this should equal,
Wait, why is kinetic energy final
this was all
after,
number
right after the slingshot is released?
that's what we're saying, because we're treating this as a system, right? We're trying to figure out, we're figuring out the motion, the energy within beginning and ending, not saying we can choose whatever our ending
Okay,
is.
so our ending is when the slingshot is released.
Yeah, right when it's back to its natural relaxed.
Okay.
Yep.
So, is there a reason
Our
why
height is at zero.
we don't use kinetic energy because 1/2 mass times velocity squared because we don't have velocity?
Well, we could, but if we don't have velocity, yeah, we can make it a lot easier just thinking about the idea that energy is conserved here
I'm
always.
just making sure I realize, so that equation for kinetic energy is only used if you would have.
Yeah, if you were solving for one of those variables, but we're solving for kinetic
So
energy
then
here.
you're just to use our really long equation.
Will we ever have a horizontal projectile problem where you have to
No.
find? Oh, that'd be really cool.
Say no to any sort of problem that we ask.
That'd be really cool.
Okay, what is the ball's speed at this instant? Now that we know that kinetic energy is that,
0.36.
What?
Kinetic energy final.
That's,
okay, so 0.36
Wait.
equals 1/2.
Change it.
What is the mass?
0.01.
Oh, 0.01, sorry.
Oh,
Solve for the velocity at that point.
So it's 8.49.
8.4.
8.5 actually, sig figs.
Oh, he's correct.
Sig joules.
Whoa.
Meters per second. That is deep.
Oh, thank goodness.
So you see how now they asked for the next step, Avery?
Yeah.
And we just used conceptually what we understand.
Yes.
Okay? Now I'm gonna add another one. This will probably maybe blow your mind.
What's the ball's radius?
If I shot this directly up from the ground somehow,
Directly.
so I've got some sort of ground, got some sort of slingshot,
Oh, direct, oh, I see.
and it's somehow shot directly up.
Okay.
What's the height?
It's like a trampoline.
What's the height?
Oh,
Times
yeah,
gravity.
focus on that.
Wait, so then.
It's actually pretty easy.
Why don't you just use gravity?
You said that's like that.
Same conditions, same energy, same everything. I'm just shooting it straight up. How high will it get?
How high? Or when?
How high is?
What's the max height it would get before telling me?
Get 83.
Wouldn't we have to know G? What is PE?
Wouldn't you have to know what?
G.
What do you mean G?
No, gravity's 9.8.
G's 9.81. Is it talking about little g or what g are you talking about?
What is
G and MGH.
Yeah, that g's always.
What is PEG?
So PEGI would be 0.
Sure, yeah.
Wait,
But think about it. Alright, let's think abstractly here. Okay? Initially I have this much energy due to elastic before I've let it go. Then I let it go. All that energy gets converted to what? Kinetic. And as it's going up, all that kinetic energy is getting converted to potential. So isn't our P, E, G, F also 0.36?
What?
Yes.
So
Oh my god.
Because at the top of the peak, what is your kinetic energy?
Oh, it'd be 0.
It's 0. Everybody hear what I just said? At the top of the peak, when you're shot some rock up in the air, its potential energy its kinetic energy should be 0 because its velocity is 0.
So then when it comes back down, it gets transferred into kinetic energy.
Yeah, when it comes back down, its kinetic energy right before it hits the ground should be 0.36.
See, this makes me so mad because like I want to go try this.
That makes me very
But
upset.
it's in a vacuum, so I can't.
Yeah, I know.
I thought we were using
Isaiah?
Like, is it
never mind.
Okay, so if our PEG is 0.36, our mass is 0.01, right? Our G is 9.81, that's always our constant. What is our height?
3.7.
3.7.
3.7 meters. That's how high.
Wait, what equation is that?
I thought we were gonna use like one of the like chapter 1 equations. I tried to use that.
I honestly wanted-
You maybe could.
See, that's what I was talking about. If you combine the slingshot and do a horizontal projectile one, you could find a change in x by only knowing what you know in the problem right now, and that'd be really cool if we did that.
No.
Like for like an extra credit problem or something.
I actually
substitution.
I'm blown away by this.
And you wouldn't have to do substitution. You would just give this change in x problem up here.
Would only
all your
find
stuff, 3 points of stuff down. I want.
Basically,
Such a waste, right? Now, I'm guessing you could get it. This guy is just like, yeah, it's like a mouse trying to pull it down.
Actually, it's not a waste. You can convert it.
Okay, so we did mathematical. Hey. We did mathematical figuring this stuff out. And then we simplified some stuff by doing it conceptual.
What about the spiritual aspect?
What about the spiritual aspect of it?
Dude, I figured it
Energy is
out.
conserved because God can create. Only God can create or destroy matter. No one else.
Think of potential energy and kinetic energy like people before Christ. Converting. So converting potential energy to kinetic energy is like converting a sinner to a Christian. You still have the same amount of people. They're just in their new bodily form.
I know. And now they're in working movement for Christ. Yes.
Haven't we like
the best thing in
exploded atoms before AIDS?
Haven't we exploded an atom?
If Jesus
Yeah.
gives you an AIDS.
so does that still